Welcome all. Very happy to see you all here. I'm Sanjay Shakotai. I am the director for the Center of Generative AI at UT Austin here, which works closely with the machine learning lab, which Adam Clivans directs and he introduced yesterday. So MLL is the umbrella organization at UT. It's the home of essentially all of ML here. Focuses on foundations, applications of biology, astronomy, computer systems, business applications, and so on. It's a broad organization. It's a campus-wide broad organization. And the Center for Generative AI is sort of the compute arm of the MLL. So we have 600 Grace Hopper 200 GPU cluster. It's Vista, which serves across campus. Already it came active about 8 months back, and there are like 25 major projects already going on this, all the way from data generation to training foundation language models to fine-tuning these models to diffusion models, which are then scaled outside by commercial companies as well. So very exciting time at UT. So welcome once again to this day of the workshop. And now it's my great pleasure to introduce Ludwig Schmidt as our keynote speaker. Ludwig is a professor at Stanford and also at Anthropic and part of IFML, the Institute for Foundations of Machine Learning. It's an NSF center housed at UT led by Adam. Ludwig has amazing results over the years. Most recently, he's been working on open data sets and some of the things you might have heard of, OpenClip, Lion, and DataComp. I guess he's going to talk about that today. These are all from his lab, and so we are super excited to have him. Ludwig?
Let's see. Okay, let's see if this works. Yes, works. Perfect. Okay, hey everyone. Thanks for coming. Thank you for the very nice introduction. Always nice to be in Austin. And today I'm going to tell you about a project we've been doing with collaborators also here at UT Austin about a year ago on building state-of-the-art training sets for language models. Okay, cool. Let's take a step back. So this is an AI event. What is AI? And I think at a high level, AI consists of two main parts, the compute part and the data part. And if we think about research that we're doing in AI, often we focus on the compute part, right? Every year by now, there are thousands of papers on different aspects of optimization, model architectures, loss functions, and so on. And this is fantastic. Over the past 20 years, we've learned a lot about how to train neural networks in a better way, how to do better generation, and so on. But as we said, there's the second part of AI, the data part, and that is currently still much less explored. So this is what we want to focus on in this talk. And just to give you a little bit of background, why is it that in AI research, we traditionally focus more on the compute part and less on the data part? To understand that, it's good to think about what is the main experimental research paradigm in machine learning. And basically, one of the key drivers of progress over the past 20 years in AI has been sort of like a rigorous benchmark-driven approach to model development. What I mean by that is that we have sort of like a set of standard data sets in the community, like MNIST, CIFAR10, ImageNet, Penn Treebank. This is old now, but new data sets for language processing would be MMLU, HellerSwag, and so on. And the whole game the community plays in the end on these data sets is, here's a fixed data set, let's push up the model numbers as high as we can. And then what you get is plots like this over time. Here's the x-axis. Y-axis is model performance. I think this is an object detection data set, so model performance is MAP. Doesn't really matter. The main point is just many, many people work on this together over the years, and as a community, we managed to push up the numbers a lot. And this is fantastic. This makes it very clear what works best, what algorithms, what model architectures, what loss functions give you at the end the best performance. There's only one catch with this. In this entire paradigm, the training data always is fixed. I think this is the MS Coco data set, and the whole rules of this game are the training data is fixed, and then you can do whatever you want on the modeling side, on the algorithm side. But because the training data is fixed, in this benchmark paradigm, we never really learn how to build good training sets in the first place. Right? And this is a challenge now, because as we continue to build better and better models that we use in more and more places, like language models, the training data is actually a key part. And this is, you don't just need to take my word for it. This is from the Llama 3 announcement from last year. They say very clearly in the announcement, to train the best language model, the curation of a large, high-quality training data set is paramount. In line with our design principles, we invested heavily in pre-training data. And then you maybe want to say, okay, Llama is not the best open weights model anymore. Qwen is better. And it turns out the Qwen people said exactly the same in their technical report. So they also emphasize data cleaning, scalable synthetic data generation, balanced data mixing. So this is really cool in the sense that they are transparent. Hey, data curation is very important. But the catch is, although these are open weight model releases, none of them actually release the training data. So in these language models these days, even when it's public in the sense of like, hey, you can use my weights, and they even describe the training process, they very rarely share how they build their pre-training data set. So this is what we're going to talk about, how to build really good pre-training data sets for language models. And we are going to do this in two parts, depending on how much progress we make. First part is all going to be about language models. Second part is going to be about training data curation for multimodal models. So models that connect images and text. And if you have any questions throughout the talk, always feel free to interrupt me. Happy to make this interactive. Cool. And for now, let's get started with part 1, language model pre-training data. And just to sort of, again, give a bit more context on how important training data is for these models, it's, for instance, nice to look at the GPT series of models, right? So GPT-1 in 2018 was trained on, by now, a tiny data set, about 1 billion tokens. And then over the years, so 2019 was already 30 billion tokens for GPT-2. GPT-3 was trained on 300 billion tokens, and then GPT-4, things stopped being public, but there are some rumors and so on, and sort of like a reasonable number is that this is by now in the trillions of tokens. For instance, Llama 3 was also trained on 15 trillion tokens. So overall, this has grown by about 3,000 in only 5 years, and yeah, scaling the training data sets has been a key driver of progress here. But as I mentioned, while the training data sets are super important, even for open weight models, people are not sharing anymore how they build their pre-training data set. I mentioned Qwen and Llama already. DeepSeek, the same story. The DeepSeek paper is actually really nicely transparent in how they train their model, and they describe their techniques like multi-token prediction and so on. And then the training data set is like one small paragraph, and they don't tell you how they built that. OK, cool. As a result of all of this sort of like secrecy around training data, this research direction is still comparatively underdeveloped. And I think when we started this project in 2023, there was this tweet which nicely summarized sort of like the state of training set research around that time. Sort of like LLM data sets be like, first you start with Common Crawl, then you add C4, which is just Common Crawl again, but don't worry about it. Eye of Newt and Toe of Frog. Then Wikipedia, also in Common Crawl, but don't worry. GitHub, permissively licensed, trust us. Rule of Bat and Tongue of Dog. Books, just all the books, every archive paper, and so on. So basically around the time, people were building data sets, at least in the open, by just throwing all the data sources they could find together. And to be fair, in the early stages of scaling things up, just because scale quickly gives you gains, this is arguably a reasonable approach. You just need the tokens somehow to train your models. You need a lot of tokens. Let's just put all the tokens together we can find. This is a reasonable first step, but when you see this is clearly not optimal, or at least it's reasonable to conjecture that you can do better with a more principled approach to data curation. And good news is people very much started doing research on this. So this is from AI2. They had a closer look at the C4 data set. And then over the past 2 years, more and more papers appeared doing research on pre-training data curation. This is great, lots of cool ideas there. But the catch was everyone was doing their own experiments in a different way. So basically, every paper had a different evaluation approach, different training methods. So you had all of these different numbers in the literature, but you couldn't actually tell anymore what is best, right? So earlier I told you we've seen a lot of progress in empirical machine learning via this rigorous benchmark approach, where we had sort of like some part fixed and you innovate on the other part. And in all of these papers, basically nothing is fixed. People change the training set, but they also change the architecture they use for training, or how many flops they use for training, or what algorithm they use for training, or what they evaluate on. And so it was really unclear what data set is best and how you put all of these ideas together. And so this is where we thought, okay, let's build a rigorous benchmark for pre-training data curation. So this is this DataComp-LM project. And as you can see from the slide, this is with many, many, many collaborators. I can only highlight a few of them. So among the students here, Jeffrey and Alex are my students. Back then they were at UW. Now Alex is, and he moved with me to Stanford. George is here at UT. He is a student with Alex DeMarcus. He's fantastic. Maor was a student with Yair at Tel Aviv University. And then sort of like here we have Vaishal. At the time he was a research scientist at Apple, now at Anthropic. Achal was at Toyota Research, also at Anthropic now. Yair is at SSI, Ilya's new startup, Ilya Sutskever's new startup. Alex is here at UT, and so on. I mean, as we said, there's about, I think, 55 people on this paper. Can't go through everyone, unfortunately, but is a really awesome team. Okay, and as we said, goal was enable principal empirical comparisons of different data curation strategies. And sort of like how you can think of this project is sort of like we built 3 different parts here. The first part is, as I mentioned already, the benchmark. So we can do sort of like a rigorous comparison of language model training data. And you can think of this benchmark as our experimental platform. So once we have that experimental platform in place, we use this in order to do a ton of different experiments to compare which parts of our training data pipeline are the most important, how can we improve the numbers. And then at the end, in order to prove to ourselves that all of this actually makes sense and we understand how to build good training data sets, we took all of our findings, put them together into a public pre-training data set that at the time was state-of-the-art for training 7 billion parameter models. Okay, cool. So let's see what does it actually mean when we build a benchmark for training data curation. So as a participant, you go through this in the following 4 steps. First, you select a scale at which you want to work. So training language models is expensive, so not everyone can train 7 billion parameter models. So we have prepared multiple different scales at which participants can sort of like try out their data curation strategies and compete only within a certain compute budget. And it starts with 400 million parameter models and goes to 7 billion parameter models. And then once you have decided on a scale, now comes the part where you can be creative. Basically, you either use our pool that we provide, a large pool derived from Common Crawl, and you filter that in order to build a better pre-training data set, or you have some new data that you bring to us, and you're like, hey, this is awesome pre-training data, I want to use that. That's also fine. We have the mixing track for that. And then you build your pre-training data set, and then this is the part where your work stops, and then you pass that training data into our fixed model training code so that everyone uses the same training code. And then at the end, once you have trained a model, you evaluate it on a wide range of downstream tasks. And then we can say a pre-training data set is good if it gets good performance on a wide range of downstream tasks. Okay, so this part here is where, as a participant in this competition, you figure out how to filter pre-training data and what additional training data you would like to add. Yes, go for it.
So with that chart there, I come from a very established industry.
Okay.
And so it's like a product development cycle you would have. Are there actual dollar figures now for these type of steps so that if you start something like this, you could say, here's a budget I need?
Yeah, exactly. That's exactly the next slide. Thank you. No, thanks a lot. More questions, yes.
Quick question. So, like, if you train multiple models at the same time, so do you actually like optimize how many steps they do depending on?
Oh yeah, we spend a lot of time making sure that the trainer model step is good. So basically, we fix it for you, but we want to make sure we fixed it in a good way, because otherwise this is not interesting. But we also didn't want something where someone is like, oh, here's my new data set, and I also made 5 changes to the optimization code, because then I'm like, is your thing better, or are you better at optimizing? Is your data set better, or are you better at optimizing? I want to be convinced that it's really the data set. Yes?
So you said that a lot of people don't release their data. Presumably one of the reasons for that is they want to hide what data they're using, that it's they're using data they shouldn't be using maybe. Do you have anything here to control for that? And like, or are you fixing the reasons that people aren't releasing their data, or are you just doing the same thing in an open way?
So all the data that we provide to people in our pool, this DCLM pool, I'll talk about this more in a minute, this is all data from Common Crawl. So it's data from Common Crawl. That means it may still be copyrighted and so on, but for public research, I think this is fair use. And if you disagree, you can sue me, but no one has sued me so far. I hope you don't sue me. Please don't. And now, of course, there's also these additional data sources like pirated books and so on. If you wanted, you could train on pirated books in a mixing track. I would still be curious about the number, but I don't want to put out pirated books and say, like, please train on that. I think, actually, the importance of pirated books is probably overstated in this sometimes. This is my subjective opinion. Sorry, OK, we are back. But, I mean, you're right. There are multiple reasons why people don't publish training data. One of them is the legal liability that a company like Meta, if they say exactly what they train on, they have more people coming after them. This is sort of like not something you can fix at this research level. There's sort of like larger incentive structures at play. But I think part of the reason is also that it's just there was no established or is no established framework for doing that research, and this is something we can fix. Good question. Cool. Let's continue because someone asked about dollar amounts, and this is indeed a very good question of AI research always. So these are the different scales in our competition. So as we said, the smallest scale is 400 million parameter models, and then you train, so like chinchilla scaling, 20 times more tokens, so 8 billion tokens, so many training flops. And training H100 hours, this is not dollars, but this you kind of convert this to dollars, right? So depending on which cloud you're on, this is maybe $2 to $4 per H100 hour. So the idea being that the smallest scale, a single training run costs you maybe $50, and then the largest scale, this dash 1x is always the overtraining factor. So these are all 1x, and then we had one where we trained with twice as many tokens as Chinchilla Optimal at the 7B scale, and then it's 7,300 H100 hours, and then it's $14,000 for a single experiment, which is definitely getting expensive. But the idea with all of this is that you can do most of the experimentation at the smaller scales, and then you only try out the promising ideas at the larger scales. And this is how a lot of AI research works now. Does this answer your question? Oh, you mean like where the H100 hour? Compute time, yeah. Yeah. Energy, and like, I mean, you also need to buy the chips and so on. Yeah. Cool, excellent, good. So these are the competition scales we have. Now the big question obviously is like, does this make sense to experiment at the smaller scale? Like, it's always nice if it's cheaper, but is it actually predictive of results at larger scale? So we did experiments on this, and on the x-axis here, you see the performance of different training data sets. Every marker here is a model trained on a certain data set. And on the x-axis, we have performance at scale S. We have 3 colors here. Every color corresponds to a different scale. Blue is our smallest scale, 400 million. Orange, 1 billion scale. And then green is the 3 billion scale. On the y-axis is what we care about at the end, or one of the things we care about at the end, the performance at the largest scale, 7B1x. So overall, what we would like to see is that performance at the small scale is nicely predictive of performance at the larger scale. And sort of like what you can see in these plots is that first order, this is very much the case. Like for instance here, the green color, this is an almost perfect linear trend. So the 3 billion scale is almost perfectly predictive of the 7B scale. This makes sense because the gap in compute is comparatively small. But even for the smallest scale we have, the 400 million scale, the blue line, these points here still stand out as clearly better than these points over here. And this is, again, predictive of what's happening at larger scale. So this is also what we did ourselves when we worked in this framework. We did most of our experiments at small scale, and then only at the end did a smaller number of runs at the larger scale. Good. I mean, so this is all of the theory and how we set this up. Let's see what do you actually get out of this if you follow this sort of like this paradigm to training data development. And this is summarized in these two plots here. Lots going on in the plot, so let's go through it step by step. So on the y-axis here, we have how good the models are. Every point in these plots here is one model we trained or others trained on a certain data set. Y-axis is how good the model are. This is an average over 20 evaluation data sets for natural language understanding. Here, MMLU is one specific one that we broke out because it's one that people look at a lot. X-axis is the amount of training compute you put in, measured in flops. So as always in language model training, more flops, so moving right on the x-axis means better performance. The key question is, for a given amount of flops, who has the best model? And now the nice thing is that the orange line here, which is our training set that we built, DCLM-Baseline, this is indeed on top of all the other models here. So for a given amount of flops, DCLM-Baseline, our training set, was the best model, the best training set in mid-2024 when we released this paper. And so like to illustrate how much this improved our prior models, one thing that is nice is, for instance, here, this point in the top right, the red X here, this is the Llama 3 8B model. So this was trained by Meta. And we get to almost the same performance, so almost same y-axis value using 6 times less compute. So overall, the more efficient, the better data curation enabled us to train a model with the same data quality using substantially less compute. Of course, ideally, we would have liked to train a better model, but we are not a trillion-dollar company, so we couldn't train a better model, but we could show that we get to the same performance level with less compute. And then obviously, what we hope others are doing, which is indeed happening, are picking up these ideas and then going from there to scale this up further and train better models. And maybe a couple more points to highlight here, FineWeb EDU and Olmo. So like this line here is FineWeb EDU. This came out around the same time from Hugging Face. I guess my laptop is sometimes going to sleep. So we are also clearly better than FineWeb EDU, and we are better than Olmo, which is another open data set from AI2. Cool. Any questions about this plot? Nope. OK, cool. Then, so we have established we get state-of-the-art performance. We can improve by a lot. Over the Llama training set, for instance, how did we actually do this? So what we are going to do for the rest of the talk, basically, is step by step go through how we build a state-of-the-art language model training set. And the starting point for all of this is Common Crawl. I'm sure many of you have heard of Common Crawl. This is an extremely impactful project for AI research. What Common Crawl started out was actually not at all AI related. They started out building a public non-profit crawl of the internet to build open source search engines. I think this open source search engine vision never really panned out, but Common Crawl had a lot of impact in other ways now. They have been doing this for almost 20 years now. In the total crawl archive they have, it's about 250 billion web pages, and this is all stored in one gigantic S3 bucket with about 10 petabytes of data. And every month or so, they release a new update with about 3 billion new web pages these days. And what we did is basically take all the data from Common Crawl, extract the text from the HTML pages, and this gives you a starting point of about 240 trillion tokens. OK. To illustrate, yes?
Does Common Crawl store the data itself or just the links?
They actually store the data. So like they have stored all the HTML that they downloaded as part of their crawl, which is important because for stuff they crawled in 2008, probably a lot of the actual websites would be by now different or they would have disappeared. So this is why it's so much data, why it's 10 petabytes. I guess Amazon is one of the sponsors. Thanks on behalf of Common Crawl. I think they get the bucket for free. Yes, question.
On a similar note, how do they handle a web page that does change periodically?
Oh, yeah, they have that multiple times in the crawl. Like some of the 240 billion web pages, some web pages appear multiple times. I think it's important, let's say, I don't know what, CNN.com, that will probably appear in many snapshots. Good point. Yes?
How many of these 240 billion are unique tokens?
How many, oh, you mean like what happens after deduplication? Yeah, this is a great question. We'll get to deduplication later. I can't tell you what happens when you deduplicate at the very first step here. Partially when we did this, we computationally couldn't afford this because dedupe is a pretty expensive step, so we only ran dedupe after filtering. So yeah, let's talk about it when we get to the point. Good question, thanks. Okay, this is Common Crawl. Sort of like to illustrate how important Common Crawl is for AI development, I thought I would repurpose this nice XKCD comic. So this illustrates the software stack that we use in our daily lives, all modern digital infrastructure at the top. And there are these funny projects here, a project some random person in Nebraska has been thanklessly maintaining since 2003. And all of modern software rests on this project. Like every now and then, people find like a big security vulnerability in a library, and then it turns out everyone has been using this library, and there's one guy maintaining this half time. In Common Crawl, it's at least 2 people for the longest time. Now it's more. For the longest time, this has really been just 2 people, one technical person doing the crawling and one person for running the organization. And yeah, they had a ton of impact. I think nowadays people go beyond Common Crawl, but I think for a long time, a lot of these early language models like GPT-3, they were really just trained on Common Crawl largely. Okay, cool. So, but as we said, Common Crawl, what they do is only download HTML. One important step in these pipelines is getting the actual page content that is training relevant out of that HTML. And this step is called HTML extraction. Actually, Common Crawl does this. They provide the so-called wet files. This is one way of doing extraction. But sort of like in the spirit of like, let's look very closely at every step on the pipeline and see how we can improve. We wanted to understand, can we improve over what Common Crawl does with the wet files? So we ran 2 other libraries that people have used for HTML extraction, Resiliparse and Traffilatura. And those are the results. Just to make sure we can read these tables, there will be more of them. These columns here are our evaluation suite. And for most of it, just look at the core column. This is the roughly 20 data sets for natural language understanding. We have extended also, which is about 50 of them. Extended tends to be a bit more noisy, so we more often looked at core. And then what you see is that these libraries like Resiliparse or Traffilatura give you substantially better performance for a given compute scale. So these experiments are at the 1 billion model parameter scale, trained on about 20 billion tokens. And we want to see, okay, what works best? And it's clearly one of these 2 libraries. So we ended up using Resiliparse because it's almost the same performance, but it's about 8 to 9 times faster than Traffilatura. Good, so this was step 1. We need to get the data and then do the HTML extraction. The most important step in these pipelines is the data filtering. So as we said, we have a ton of tokens, about 240 trillion from Common Crawl. Now we need to actually decide which of these tokens should we keep and train on. And that's data filtering. And so like a starting point for us, we used, or like overall what we used is a combination of heuristic filters and a train classifier. So the high level, how you can think about data filtering is 2 different approaches. One approach is that people look at the data, they see, oh, there are certain data, like pages that clearly aren't high quality data. Let's come up with some handwritten rules, handcrafted heuristics to filter out data that looks bad. This is indeed what people have done successfully, for instance, in this refined web paper, and they came up with a ton of different heuristics for filtering out documents based on page length or language, how often filler words appear, in-document repetition, and so on. This is a good starting point. But what we found, what is very important as an additional filter, is using a train classifier to decide what is good training data and what is bad training data. Right? So this is now we are doing machine learning in order to curate the training data set for another machine learning model. And so what we need to figure out is what kind of model do we use to classify our training data, and what training data do we use for our training data classifier, right? So what are examples of high quality data, and what are examples of low quality data? Basically, how you train these document classifiers, so you give it some positive examples, some negative examples, and then it's a binary classification problem. Okay, and so what we did there, as a starting point again, was just try basically everything that's out there. We wanted to build a state-of-the-art data set. So as a starting point, always need to understand what is the state-of-the-art and how do different methods compare. So here, this is the refined web reproduction. Our reproduction of refined web gets core 27.5, again at the 1 billion model parameter scale. And then we tried a lot of different things that we came up with, or others had come up with. For instance, PageRank could make sense, right? PageRank very widely used, or at least for a long time has been widely used for search, but that's worse than doing the refined web filters. SEM-dedupe, some basically semantic deduplication, you can use this for filtering, but also worse than refined web. And we did a lot of other things, different features, you can use language models for classifying, you can use perplexity. What worked best for us was the fast text classifier library combined with a specific set of positive examples. Okay, so fast text is a relatively simple text classifier. It's only using bigram features. And then we trained that fast text classifier on a combination of Open Hermes 2.5 and the explain like I'm 5 subreddit as positive examples. So this is a bit random. So like Open Hermes 2.5, this is an instruction tuning data set. And then the explain like I'm 5 subreddit, this was sort of like basically relatively simple training data because people explain things in an easily understandable way. We thought this could be high-quality data from the purpose of training a model. So we use this as positive examples. And this works substantially better than any of the other methods. So just for context here, you could ask, OK, like how different is 27.1 to 30.2? These are relatively small absolute differences, but they correspond to large compute efficiency improvements. So like this 6 times more efficient that we have compared to Llama at this scale corresponds to maybe a 3 to 4 percentage point difference in this core metric. Yes?
So just PageRank, core and extended, are there units these numbers?
Oh, these are all, I mean, it's a little funny because we center some of these metrics. You can think of all of these as numbers between 0 and 100. Okay. Yeah. Cool, thanks for clarifying. Okay, so fast text works really well in this library. And one thing that was surprising to us is how important the training data for your filtering model is, right? So even when you fix to one specific text classification method, here now fast text, we tried a bunch of different data sets as high quality data. So the low quality data, the negative examples for the classifier are always just random samples from our data pool. The positive examples are, as we said, either Open Hermes or plus explain like I'm 5. We used Wikipedia as high quality data. Open Web Text 2, this is GPT-2 basically, and then an approximation of the GPT-3 training data. And what you see here is that, for instance, or concretely like this Open Hermes plus explain like I'm 5, positive example, the corresponding classifier, does much better than all of the other data filtering approaches that people had tried before. And so again, just to put this in context, doing refined web, so no model-based filtering at all, gets 38.3 on core at the 7B scale. So this is 7B scale now. So all of the prior data filtering methods actually did worse than not using a model-based filter at all. Like here, our thing is the first one in a model-based filtering, the train classifier actually does better than not using a train classifier at all. Okay. And some of these results are a little bit counterintuitive when you look at them. And so we wanted to understand a little bit better, are humans even good judges of training data quality? So like one thing that people had often assumed in this field is, in order to build a high quality data set, at some level you have humans look at the data and make quality judgments. This is good training data, this is bad training data. And as a first approximation, this is reasonable. However, what we found is, if you really want to build the best possible training sets, then you need to go beyond human quality judgments. Like humans can't actually tell what is good training data for a language model. And how we did this is as follows. We took 500 documents from our corpus, and we had several of the collaborators on the project label these 500 documents as good or bad training data. And the people really tried, in the sense like these were motivated, well-qualified PhD students and research scientists. They wanted to do the best possible job. judging whether a given document is good or bad training data. And then we thought, okay, great, now we have these 500 documents with human annotations. Let's see how much do these human annotations agree with how good a training set really is for training a model. And this is what these plots summarize. So on the x-axis is the agreement between the human annotations here that we collected and what a given scoring model predicts. So every marker in this plot here corresponds to one model trained with one specific data filtering method, with one specific data scoring method. So what you see is that this is like this model here, the blue point, this comes from the Ask LLM data curation method, and that has large agreement with the human annotators, but this is the worst on the y-axis. The y-axis is what you actually care about. The y-axis is how good is the models when you train on the corresponding data. And so what you see is, okay, blue point, good on x-axis, but pretty bad on y-axis. And then all of these orange points, these are variants of fast text. And what you see is that the best variants of fast text, the best points on the y-axis, you can't really tell them apart from the x-axis. So yeah, in the end, language models do learn differently, and some of the resulting findings are counterintuitive because you look at the data, it doesn't actually look like the best training data, but it's better for the models to learn. Cool, okay. So we have 5 minutes left, so we can quickly talk about deduplication, because someone asked about this earlier also. Again, deduplication, one important step in your pipeline. Once you have done all your data filtering, you want to remove documents and content of documents that appear several times. Like there are going to be some things like, I don't know, like the Declaration of Independence that appear on many websites. And conventional wisdom, at least, is that if you train on the same document many times, this is bad for the model. It will overfit and generalize worse. So you need to remove near duplicates. And again, there are many different variants how you can do this. You can look for exact duplicates. You can use algorithms like min-hash, suffix array, Bloom filter, and so on. And again, we tried all sorts of variants of this. And then what we went with for the paper is something based on Bloom filters. I think in retrospect, this is one thing where we made a wrong choice. By now, I would recommend people do min-hash. Basically, at the time, min-hash was hard for us to implement, couldn't scale it up properly, and then it was like towards the end of the project, when it was already too late, a student finally learned Rust and wrote a really high-performance implementation of min-hash, and then everything was much better. So one learning for us here was like, some of the things you just can't do efficiently in Python. Like some of this data processing becomes expensive enough that you need to do it in a more efficient language like Rust. Cool. And this is also, like, just for context here, dedupe is a tricky part to experiment with, because as I mentioned earlier, all the other, or like generally this paradigm here is to do experiments at smaller scale. So you train on a random subset of your data. The tricky thing with duplication is that IID subsampling does not preserve duplication statistics. If I take a data set, I IID subsample it, I have fewer duplicates. And this is why I think this entire deduplication area is still something where more research is needed. Cool. OK, so let's put it all together and look through the steps in our data curation pipeline. So we started out with our pool from Common Crawl, 240 trillion tokens. Then the first step are the heuristic filters from refined web. And then about 14% are left. The rest gets filtered out for various reasons. Then we do dedupe. That filters out about 1/3. And then we do our model-based filtering and throw away another 90% of the data. So overall, at the end, we are left with about 1 to 2% of the data, about 1 trillion tokens. And this is the data set we train on. And one thing you clearly see here is, at the moment, this is a very lossy process. Like overall, we filter down the original corpus by roughly a factor of 100. And we could afford doing that because Common Crawl is just so big, and we wanted to find the very best tokens to train on. But as people scale up models more and more, I think one important question is, how can you improve the recall of this process? Because if we make the models larger and larger, at some point, we'll run out of internet data. OK, cool. We have like 1 or 2 more minutes left, right? Good. So One more finding that I wanted to highlight quickly because it's counterintuitive also is again around high quality data. So prior work had found that if you combine common crawl derived data with high quality data such as Wikipedia, books, Stack Exchange, and so on, then you get a boost in performance. And we could indeed reproduce it. Like if you take data sets like C4, Llama, and Refined Web, and you add in these extra data sets like Stack Exchange, Archive, and so on, you do see gains. 2 percentage points on C4, 1.7 on Llama, 1.4 on Refined Web. What we found really confusing is once we added Wikipedia and Archive and Stack Exchange on top of our data set, performance actually got worse. So somehow we had managed to filter the web good enough so that adding these high quality sources, at least by name, into our data set led to a worse data set overall. As I said, so some of these data curation things can be quite counterintuitive. I think that's exciting because that means we don't really understand what's going on yet, and that means hopefully we can make things better. Yes?
If common crawl has crawled the whole web, shouldn't it already contain all the other stuff like Wikipedia and Stack, or no?
Yeah, that's a good question. I don't think actually that common crawl contains all of Wikipedia. Because I mean, C4 is also common crawl based. Yeah.
Were you, I mean, I imagine you didn't, but were you able to kind of like grade what level the quality is like when you were done with it? So when you attempted to look at things that were already labeled high quality, you could see if it was like the same standard?
So a good question. So one thing we did was we had again sort of like one student who was looking at different filtering methods. He looked at sort of like what do different filtering methods rate as the best documents according to the respective filtering method. And again, subjectively, he preferred a filtering method that actually led to worse training data. Like when you train a model on it, was a worse model. So yeah. Cool. Okay, we do need to wrap up. So I just quickly want to highlight that since then there has been more follow-up work, like one nice paper from NVIDIA, Nemotron CC. They improve over DCLM by changing the heuristic filtering step. Hugging Face continued their Fine Web line of work, and they released a data set with a bigger focus on multilingual on languages other than English. And yeah, more people are building on our data sets. And so like the second part of the talk, we just don't have time for. This is okay. This is where I was planning to tell you about all the same stuff, but now for the multimodal domain. Basically, actually we did this first. We first built a similar benchmark for multimodal data curation, got nice results, and then we thought, okay, we should do this for language. But we don't have time for that. It's okay, let's conclude. Yes, as we said, training data is key for foundation models, both in language and in the vision domain. And you can see large gains by doing data curation in a better way. I think in order to make sure this is done rigorously from the experimental side, having benchmarks like DataComp is very important, so people compare their methods also like in similar settings, and we can really all agree on what works best. The most important ingredient in these pipelines right now, where we saw the largest gains, was model-based filtering. This was actually also true for the Lion/DataComp world, where we worked on image text data filtering first. The largest gains there also came from model-based filtering. And I think overall, this is very much, I think, early days still for data research. One thing you've probably noticed in this talk, some of the results were counterintuitive. I don't have any theory for this at all. Like everything at the moment is very experiment-driven. We have all of these tables. We try all of different things. Some things work better than others, but I don't really have a coherent overarching story right now for how to do this from first principles. So I think there's a lot of room for improvement. And if you find this interesting, you can go to our website, DataComp-AI, and I'm happy to take more questions. Thanks.
Yes, thank you. Questions?
Yeah, so have you looked at all at any kind of curriculum training, like train on the bad data first, good data later, or vice versa, or whatever?
Yeah, great question. So we haven't looked at this systematically in this project. I can tell you anecdotally, when we built our this we called it our hero run, the final model where we tried to beat Llama. For that thing, at the end, we were like, we're almost there. And then one of the students, Alex, was like really motivated to actually, so like, okay, at least beat Mistral. And then he tried a lot of different sort of like cool down phases where you take a partially trained model, and then you, for like maybe 200 or 300 billion more tokens, you have a model trained on, let's say, 1 trillion tokens. For 200 billion more tokens, you add in other data. And he did see nice gains from that. And this is basically curriculum learning. But this was, again, very ad hoc. I don't think I can say too much principled things here. Having said that, there is one nice paper I remember, I think, from someone, I forgot the name. I think this was someone's NVIDIA internship where they tried these experiments more systematically. And they also found that scheduling these more reasoning heavy things like coding and math towards the end helped them.
One thing I must have missed, a basic thing I'm confused about, is that as you showed that plot where human annotators weren't able to agree with what was useful for the training data, but when you were training the classifier, the positive examples were explained to me like I'm 5 or something. Presumably that was a human decided that those should be positive examples.
Yes, I think
isn't that slightly contradictory? Like
yes. Okay. Let's be precise. Great question. So there is the training data we use for training the language model, and there is the training data we use for training the model that's going to pick the data for training the language model, right? And it is quite plausible to me that also for our model that does the filtering, the best training data would be counterintuitive to human. In fact, I think it's actually somewhat counterintuitive. At least sort of like if you look at what people did before, people were like, oh, high-quality data should look like Wikipedia. So they were using Wikipedia's positive examples, and doing this filtering with Wikipedia's positive examples works much worse than using this open Hermes plus explain like M5 combination. So I think the high-level trend that human intuition is not necessarily predictive for how to do data curation holds both for the actual language model training and for the model, and for training the model that you use to filter. But you need to also you need to start somewhere. Yeah, exactly. I mean, sort of like, it's not like someone can give me the 1 billion perfect tokens for training this filtering models. If you could, that would be great. I would love to have those tokens.
Did you look at the importance of the tokenizer as you were either doing training or looking at, like when you're quoting how many number of tokens and so on?
It's a great question. So for this model, while it beat Mistral and sort of like was really good, we used a pretty old tokenizer from the Eluther models. They had the Pythia series of models. And we started out with their tokenizer because we thought like, okay, we need to start somewhere. And during the entire project, we were always thinking, okay, at some point we'll switch to the Llama 3 tokenizer and we'll get some nice boost because it's a better tokenizer. We never saw performance improvements by changing the tokenizer. And I don't know if we just did something incorrectly or if this is just not that important in the pipeline, but for us, tokenizer played no role. So basically you're saying if you want to train your own language model from scratch. Yeah, if you want to train your own language model from scratch, I think it's still true that DCLM, our data set, is one of the best, if not the best, starting points for training language models from scratch, because there are models. Okay, one thing that has happened since then, for instance, Qwen released the Qwen models, and Qwen 2.5 is substantially better than our model at the 7B scale and substantially better than the Llama models at the 7B scale. But Qwen 2.5 is again closed data, open weight, but closed data, and they don't even tell you how they built their training set. So if you're really looking for things that are open data, then I think our thing is still among the best. And you do need to go through this process of like training your own models. If you want to improve over DCLM, doing your own data curation, yeah, it's a lot.
Okay, then let's thank Ludwig again for the talk.